chapter 5 of this course, chapter 10 in the textbook, does contain quite a bit of math. There are several different equations, and here's how you go about applying them. Really, there are only a couple of different types of question that you're going to be asked. And the first type of question is a what changes when something happens. So a question will be, here is a balloon, it has a pressure and a volume. What happens when I change the volume of the balloon? Okay, those questions that ask you to find a change fall into three categories: Boyle's law, Charles's law, and Avogadro's law. Boyle's law, remember, is P1V1 equals P2V2. It's going to give you a pressure and a volume in the question and then ask you to find the missing number when it states what a new pressure or a new volume is. So if P1V1 equals P2V2, then P2 to solve for the new pressure is P1V1 over V2. To solve for the new volume, that's P1V1 divided by P2. Charles' law talks about the volume to temperature relationship. So a Charles's law question again asks for a change. What happens? Something new. It will give you a volume and a temperature. And then it will ask you, what is the new volume at this new temperature? Or at what temperature must I be at to create the new volume? So V1 divided by T1 equals V2 divided by T2. That's our expression for Charles's law. And if you want to solve for V2, V1 times T2 divided by T1. Remember, when you move anything across the equal sign, it changes from being a numerator to a denominator, or from being a denominator to being a numerator. So if I want to isolate V2, which is here, I have to move the T2 across the equal sign. So it goes from being a denominator on this side of the equal sign to being a numerator. V1 T2 divided by T1. If I want to solve for the new temperature, T2 equals V2 T1 divided by V1. Exactly the same approach for Avogadro's rule. Volume to moles. The volume-mole relationship is this way. It's very similar to Charles's law. And so the new volume is V1 N2 divided by N1. The new number of moles, N2, equals V2 N1 divided by V1. Those are the types of questions. Look for them. They ask for a change. The other kind of question that you're going to see is a question that gives you lots of information, but there's one number missing. And those are going to be ideal gas law questions. And the ideal gas law tells us PV equals nRT. So lots of information in this question. The question won't necessarily tell you the value of R. That's a constant, and you should be aware of it. On a written test, it's printed on the front cover. On an online test, it is either in the table of constants at the beginning of the test, or it's written somewhere close by in the test. Okay. But they're going to give you all of these values, the P, the V, the N, and the T, except one of them. One of those numbers is going to be missing. So if the missing number is pressure, that means I've got to move the volume across the equal sign. So P equals nRT over V. If I want to solve for volume, V equals nRT divided by P. If I want to solve for the number of moles, that means moving this R and T across the equal sign, so it becomes denominators now. N equals PV over RT. And if I want to solve for what the new temperature is, PV over NR. Tricks for the ideal gas equation: pressure must be in atmospheres. If it's given to you in the question in millimeters of mercury, you must convert it to atmospheres. 760 millimeters of mercury is 1 atmosphere. Volume must be in liters. If it's given to you in the question in milliliters, you've got to convert that into liters. N is the number of moles. If the question tells you a mass of gas, you've got to turn that mass into a number of moles. Moles is mass divided by formula mass. R is a constant, and T must be in Kelvin. Now there's a trick to R as well. If you just go and look up what the value of R is on Wikipedia, you'll find that the universal gas constant has more than one value. That's not what constants are supposed to do. Constants are supposed to have one value. It's got different values depending on which units it uses. So you'll need to look for the value of R that is liter atmospheres per mole per Kelvin. Liters, atmospheres, moles, Kelvin. Okay, and that's 0.0821 liter atmospheres per mole per Kelvin. All right, there are two other types. They're going to be an effusion question. The word effusion will be in the question, and that will be a Graham's law question, or mixture will be in the question, and that's a Dalton's law of partial pressures. These are the big two. Okay, so here's our first question. A 1 liter container of helium has a pressure of 0.85 atmospheres. What will be the new pressure if the volume is reduced to 0.50 liters? Okay, this is a question that is asking about a change. It gives us two numbers, a pressure and a volume, and then it asks us about what happens at the new volume. That's Boyle's law. P1V1 equals P2V2. And we know how to rearrange that to isolate P2. P2 is equal to P1V1 divided by V2. So I just take the numbers that are in that question and I put them into my formula here. My P1 is 0.85 atmospheres. That's the pressure at the beginning. My initial volume is 1.0 liters. And my new volume is 0.5 liters. And I notice that those liters cancel each other out and give me an answer that's in atmospheres. 1.7 atmospheres. Okay, at the end of a question, it's always good to ask yourself, does my answer make sense? Because it's a calculation, and your calculator may have assisted you in this and you're not 100% sure. Does this make sense? What is supposed to happen to the pressure of a gas when volume is reduced? When you contract a volume, pressure is supposed to go up. Is my final pressure higher than my initial pressure? Yes, it is. So I'm likely to believe my own answer. Okay, here's a second question. A balloon of argon occupies 2.7 liters at 25 degrees Celsius. What will be the new volume at 35 degrees Celsius? Again, it's a question about a change. This change includes volume and temperature. This is Charles's law. V1 divided by T1 equals V2 divided by T2. So the first thing that we're going to do is get V2, because the question is asking about the new volume on its own by moving T2 across the equal sign. So T2 times V1 divided by T1 is now equal to V2. And that's when you think about putting the numbers into the equation. But you've got to stop. This is Charles's law. It relates volume to absolute temperature, not to Celsius. Volume is related to Kelvin. So the thing that we have to do now is change our temperature. The temperature scale that we use in the gas laws is in Kelvin. 0 degrees Celsius is 273 Kelvin. So all we have to do is add 273 to both of the numbers in the question. T1 now becomes 298 and T2 now becomes 308 Kelvin. So 308 Kelvin times 2.7 litres divided by 298 Kelvin, and you can see that those kelvins cancel each other out. That gives you an answer that is in litres, and my new answer is 2.8 litres. That's larger, not significantly, but larger than the volume that I started with. So at this point you ask your question, does that make sense? I took a gas and I heated that gas up. What is supposed to happen to gases when they get hot? They expand. This number is probably right. Here's our next question. 11 grams of carbon dioxide gas is held in a 2.5 litre container at 50 degrees Celsius. What is the pressure of the gas? So this question doesn't ask about change. It gives us lots of information and then asks us to find the missing number in this case being pressure. So look, there's a temperature in there and a volume, and that's an amount. It isn't a mole amount, but it's an amount. This is going to be PV equals nRT. It's an ideal gas question. So the first thing we're going to do, because we need to solve for pressure, is to rearrange PV equals nRT to solve for P. P equals nRT divided by V. And then before I put any numbers into this equation, I always make a table off to the side of this calculation. And that table contains all of the variables and constants. Okay, PV equals nRT. I'm going to put everything in this table. What is pressure? Well, it's in atmospheres, but I don't know what it is. It's part of the question. What is volume? Volume is 2.50 litres. It needs to be in litres, and thankfully this question gave us the volume in litres. If it gave it to us in millilitres, we would have to do the conversion from millilitres into litres. N is the number of moles. That's not given to us in the question, but it is implied because they give us a mass and they tell us the name of the chemical. The name of the chemical is carbon dioxide. That is CO2. CO2 has mass, carbon on the periodic table has mass of 12, and oxygen has mass of 16. The formula mass of carbon dioxide is a 12 and a 16 and a 16. Carbon dioxide has a formula mass of 44. Moles is mass divided by formula mass. Mass is in the question. It's 11 grams. Formula mass is implied in the question because it gives us the name and or the chemical formula of the molecule that we're looking for. So 11 divided by 44 is 0.25 moles. R is the universal gas constant, and when it's written in its form of litre atmospheres per mole per Kelvin that we need for this form of the equation is 0.0821. Temperature is given in the question. Temperature is 50 degrees Celsius. But again, we don't use Celsius in gas calculations. We use Kelvin. So I'm going to convert Celsius into Kelvin by adding 273 to my number. So my 50 degrees Celsius becomes 323 Kelvin. Now I can put those numbers into my equation. And 0.25 moles times 0.0821 liter atmospheres per mole per Kelvin times 323 Kelvin divided by 2.5 liters. That liter and this liter cancel, that mole and that per mole cancel, that per Kelvin and that Kelvin cancel, and it gives me an answer that is in atmospheres. My answer is 2.65 atmospheres. Okay, here's a question that is a little bit more complicated. A mixture of gases, 5 grams of oxygen and 5 grams of chlorine, are both held together in a 2-liter flask at 0 degrees Celsius. What is the pressure inside the flask? This is a question about a mixture of gases. So at some point, this is a Dalton's law question, because Dalton's law says that the total pressure is the sum of all of the individual partial pressures. But I don't actually need to find the individual partial pressures to get to this answer. You could set up an individual PV equals nRT for this number of moles, 5 grams of chlorine, and for that number of moles, 5 grams of oxygen, find 2 individual pressures and then add them together. Or you could go and say that the total pressure has arisen from the total number of moles. Dalton says that too, that the total pressure is the sum of all the individual partial pressures, which are responsible because of the number of moles. So P total equals N total RT over V. So I need to do a couple of mole calculations. Again, pressure is missing. That's what we're solving for. Volume is in the question and is given to us as liters. That's good. It means we don't have to alter that number. I don't have a mole amount for either of the components, and I don't have a total number of moles. So knowing that moles is mass divided by formula mass, I'm going to find the number of moles of oxygen, and oxygen gas is O2. Each oxygen weighs 16 grams per mole, so that is 32 grams per mole for an O2. 5 divided by 32 is 0.156 moles. Chlorine, on the periodic table, an atom of chlorine is 35.45. So a molecule of chlorine weighs 71 grams per mole, significantly heavier than oxygen. So 5 grams of chlorine is not going to be nearly as many moles as 5 grams of oxygen. So the number of moles of chlorine is 5 divided by 71, which gives me 0.070 moles. Let your calculator at this point of the equation give you more decimal places than you deserve. Only whittle it down to the absolute number of significant figures allowed in this question at the very end. Don't round up while you're doing the calculation. So if I add those two numbers of moles together, I get the total number of moles in my gas. So 0.156 plus 0.07 equals 0.226. R is the universal gas constant, 0.0821 litre atmospheres per mole per Kelvin. And the temperature again is given to us in Celsius at 0. I'm going to add 273 to that to make it a Kelvin. I'm going to put those numbers for N total, R, T, and volume in the calculation, and it's going to tell me that the total pressure for this gas is 2.5 atmospheres. The obvious follow-on question then is how much of that total pressure was due to one of the gas components. I had oxygen and chlorine. So what if I asked, what is the pressure due exclusively to oxygen in this gas mixture? The pressure of oxygen in this mixture is the number of moles of oxygen times R times T divided by V. So all I have to do is substitute in that number of moles from right here. And I find that of the 2.5 atmospheres of total pressure, 1.74 of that belongs to the oxygen. That's a disproportionate amount considering that they are both in the same mass quantity. But mass doesn't tell us moles. Mass divided by formula mass tells us moles, and because chlorine is so much heavier than oxygen, you need more mass to give you the same number of moles. So a smaller amount of oxygen gives me more moles. Okay, this question is unlike the others. It is a question about effusion. It specifically has the word effuse in it, which means we're going to be using Graham's law of effusion. It takes 2 minutes and 11 seconds for a mole of oxygen gas, O2, to effuse through a hole. How long will it take a mole of chlorine gas to effuse through the same hole? The mole quantity in this question is completely immaterial. It's just hinting at it's the same amount, okay? Same amount of gas. The actual number of moles is not important. What is important is that minutes is not a decimal form of time. So we cannot put minutes or hours into a calculation. We're going to have to change our 2 minutes and 11 seconds into seconds. 60 seconds in a minute, 2 minutes is 120 seconds, plus the 11 on top is 131 seconds. Oxygen has a formula mass of 32, O2, 2 16s. Oxygen has a mass of 16 on the periodic table. Chlorine, Cl2, has an atomic mass of 35.5, so 2 of those, 71. Graham's law of effusion, when written as a time, reads that the time taken for chlorine divided by the time taken for oxygen would be equal to the root of the formula mass of chlorine divided by the formula mass of oxygen. So just a very small rewrite then to isolate the time for chlorine on the left, move the time for oxygen from being a denominator to being a numerator. So the time for chlorine is my time for oxygen in seconds, times the root of 71, the formula mass for chlorine, divided by 32, the formula mass for oxygen. That's 131 times 1.49, 195 seconds. Okay, so we've never done effusion experiments before, so we don't really have anything to grab onto here, but we can use logic. What is supposed to happen to the time it takes for a gas to get through the hole if that gas is heavier? It's supposed to take longer. And the fact that the lighter gas goes through the hole at 131 seconds, the heavier gas goes through the hole at 195 seconds, that suggests that our calculation is correct.